Hi guys, so today we're going to be going over AP Chemistry on Khan Academy. Not the whole thing, of course, it's just going to be Unit 4, Chemical Reactions. So I haven't watched the videos, as you can see. I was just reading the Zoomdal chemistry book online. So it was the same chapter, so it covered most of the same concepts. I watched one or two videos here. Uh, and all I've got left so far in this is the introduction to titration, and besides that, the unit test. So let's begin. Actually, let's just go all the way from the start, from net ionic equations. We'll do all of the things once, all of the all of these little quizzes, and then once we're done with those, we can uh yeah, once we're done with those, we can just do the unit test and then see. Okay, so the first one here is, one second, let me check if my audio and everything is working. Okay, yeah, it is working, so that's good. And yeah, let's go over it now. So the first one is, which of the following best represents a dissolution of uh yeah, of cesium, like, okay, so CS2, CO3 and water. I think that's like cesium carbonate. I'm not sure. But okay. Yeah, so when you're like, if something is dissolving in water, then, and they're looking at net ionic equations, right? So we'll have this, the reactant will just be this in the solid state. Wait, it's a bit hard for me to write. Okay, it's working, but it's very laggy, it seems. So we've got the reactants correctly put there. Now, as for the products, okay, this is like very slow. I don't know why. The products, so it's going to be in an aqueous solution, and the ions are going to be broken apart. So we'll have cesium here. Um, the thing is, we need to be careful of the charge here, right? So we need to obviously balance the charge. So this one is wrong. I don't know if my X is even showing there. Okay, yeah, that's wrong. This is also wrong. Everything doesn't break up, and the charges here aren't balanced either, so that's wrong. And yeah, this one. So D will be the correct one. The first one we already said was wrong. So the answer should be D. So let's select that. Okay, next one, aqueous FeCl3 reacts with, what is this? Potassium. I forgot. I don't know the names too well, so that's fine. And potassium chloride. So aqueous potassium chloride. Solid precipitate of this. So that will be put in the solid state, which we can see in all of these three. So that's correct. Aqueous reacts with the aqueous. And okay, we want a balanced net equation. Okay, let's just write the whole thing then to start off. So we'll have FeCl3. Okay, this is, I don't know what's going on here. It's horrible. So, let's just try to do this verbally then, because this is going very poorly. So it'll be Fe3 plus aqueous, and then then there'll also be Cl3 uh minus, or like 3 minus then, and aqueous chloride. Okay, so sorry, 3 Cl minus, so 3 chlorine minus, then aqueous. So the chlorine from aqueous iron chloride will cancel with this chlorine, so we're just left with aqueous KO. And actually, yeah, so we'll just have um wait, I think a lot of things will cancel out. So we'll have aqueous iron, right, which will be here, and then we'll have aqueous 3OH. That should be correct, and everything else will cancel out. Okay. Yeah, I wish I could write with this, but wait, I'll disconnect the tablet for a bit and plug it back in a minute or two. Hopefully that will help, but I'm not sure. And it is working if I just don't use the tablet, so hope maybe it's just an issue with that. Okay, here. So we can keep the solid here, obviously. The spectator ions. Okay, that's what they're asking for. So let's see what remains in an aqueous solution throughout. That's basically what it is, right? So there's K2. not Cr, not O4, but there is NO3 and not Ba. So it's just K2, or well, we won't say K2, we'll just say K plus, potassium plus, aqueous, and uh, what is that? Nitrate. Okay. So for this, the net ionic equation, he writes this. So the solid stays there, which is correct. The charge on this is correct. And there's wait a minute. So wait, this actually does seem right, but so the charges also do seem to be right. Yeah, these charges are correct. The equation is balanced with respect to charge. The chlorine ion is missing from the equation. It should be missing because this is a net ionic equation. None of those are wrong, so the equation is correct. So with that, we're done with the first one, net ionic equations. Now let's go on to representations of reactions. I'm not too sure. This definitely wasn't in the book, at least that's what I remember, so we'll just see. I don't remember how long ago I did this, so I think it was just a few days ago, so hopefully I'll remember how to do this stuff. Under certain conditions, okay, so we need to look here. Hydrogen gas, so that these are the small things, one, two, three, four, five, six, seven of them react with uh, nitrogen, so there are two of them to form ammonia. A vessel contains or ammonium, I'm not too sure. A vessel contains a mixture of H2 and N2 as shown below. So uh, to get this ratio, you'll need three hydrogens and two of those. So you take three, you take three. So you'll have three, not three, sorry, you'll have three. So you'll have six of those, and then you'll have a bit left over. Well, wait, no, not six. What will it be? It will be six, I think. Because you need three times as many hydrogens. There'll be one, like a little bit left over as well. That's the thing. Uh, After the gases have reacted as completely as possible. So first of all, are these all showing NH3? Are they showing it correctly? The last one is not, so that's out of the question. Basically we just need to make sure that in total there are. Oh wait. Um, so the ratio in the mole should be 3 moles of hydrogen to 1 mole of nitrogen, and we do seem to have that. I think. I'm pretty sure we have that. And there's one extra hydrogen. So at the end there should be, like two extra hydrogens left here. Let's select that for now. Um, the last one is wrong. It should just be that, but I want to just make sure. Okay, so how many hydrogens are there in total? Well, one, two, three, four, five, six. 6 times 2, 12 hydrogens in total will be like reacted, divided by 3, so you'll have 4. Yeah, you'll have 4 of these. Sorry about that. Yeah, that seems correct. Okay. The rest of these will be fast. I just didn't really know how to do that one properly. So a mixture of C2H4 and O2 is placed in a container and a reaction occurs according to this equation. A particle level representation uh, is shown below. Okay, so how many C2H4s are there? What does that even look like? So there'll be two of these and one H4, but I don't see any of those. Um, oh, this is a product mixture. Okay, that makes sense. And now they're asking for the reactant mixture. Okay, so how many H2Os are there? These are all H2Os. So there are 4 of them. So that means that the entire equation, like everything's being multiplied by 2. So there are 4 of these, there are 4 of these, there are 6 of these, 2 of those. So there are just going to be 2 of the C2H4s. Or let me try to think of the name. It might be wrong, but it should be like dicarbon, dicarbon tetrahydride or something. Tetra. Okay, let it be. So how many of those are there? There are 2 of them. and they're like these things. So they're just two. So it's this one, D. They're mixed, causing a precipitate to form. Precipitate to form. Uh, okay. How many sodium chlorides will be made? One, two, three, four. So they cancel out, and we're just left with um. Yeah, so that will be a solid. Wait, no, no. What will be the solid? This is aqueous. So the solid will be BaCO3, um, which is so it's one of the last two, and they'll react together. Sorry. Oh no, it's aqueous. So in an aqueous solution, they won't react together. They'll still be left as ions, and there won't be anything like left in the middle. The CO3 gets used up in the in the precipitate, right? Precipitate. So it should just be D. Which of the following equations best describes a reaction? Okay, and let me plug in my thing now. I think it should hopefully start working, or at least work better. Okay, let's take a look here. Which of the following equations best describes the reaction? So initially we've got Cl2, 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 five of them, and three of those. And in the end, okay, wait. So this is wrong because if you look at it, there are five Cl2s here, and then there are two left there. So there are three, and there are three H2, H2, H2. So there are three H2s. So the net change, you have HCl, hydrochloric acid, or and how many of them are there? There are six. So the ratio is 3, 3, and 6, which is just 1, 1, and 2. So it's this one right here. Okay, done. Okay, that also took pretty long. This one should be easy, hopefully, but I don't want to guarantee anything. Okay, which of the following processes represents a physical change? This is just changing the state, so that's it. Which of the following chemical processes are characterized by changes in um, intra intramolecular means that it's like outside, which is wrong. Chemical processes are characterized by changes only in intermolecular forces, right? So it's B. Unless I'm misunderstanding it, because I think intermolecular, like intramural. Wait, no, maybe this is wrong. Intramural is like within a school, right? Like a sports or whatever. But intermural, I think would be, yeah, international, which means that it's like outside, I guess. So it should be this one then. Intramolecular, so that forces within the within molecules, and yeah, chemical bonds and dispersion force are hydrogen bonding. Okay, seems good. Chemical process, sublime. So this is a change of state. Separated. This is also a change of. It's not a change of state, but it's like a physical separation, or something like that, resulting in the evolution of. Okay. Okay, this is also obviously physical, so it has to be this. You're heating it, and then there's like a new gas that's coming out. You're separating them, I think. So that's you're obviously changing the composition. You're making it from H2O2 to, I think, H2 and O2. So that's definitely the chemical one. Over here into oxygen gas. So if you're breaking it into oxygen gas, that's a chemical change because OO bonds are broken and new, because covalent bonds between O3 molecules are broken and new bonds are formed. Okay, so it's definitely a chemical change. I'm not too sure why though. Right, which one seems right? Would it be an OO bond and then new OO bonds formed? Well, you need a double bond, I think, so that seems wrong. I think it's D. Then it has to be C. Let's see though. Okay, we need to determine in order for covalent bonds between oxygen atoms must be broken and new ones must be formed. So the is best classified because Okay, and new ones have to be formed. I think that was the thing. So we're trying that again, and hopefully we'll do better this time. Physical change because only dispersion forces. Chemical process. So same question as before. Next, which of the following statements comparing is most accurate? Physical processes are chemical are intramolecular, and so that again another like repeat question. And here physical change, so it'll just be this one. Again, same question as before, I think. Okay, lesson 4. Now this is, oh, I think this one requires actual calculation. So, okay, wait, I don't really know this, but we're going to try it anyway. So when heated, it decomposes according to the reaction represented above. Is initially, okay, so it should be 1.2 because it says something like, so there's 1 mole here, and now here there's 1 mole of SO2 and 1 mole of Cl2, so that's 2 moles, so you just multiply it by 2. I haven't watched the video, I haven't read that in the book yet. This has something to do with gases, obviously, and I haven't read that chapter yet, so I just know this from here. But I can't explain it, I just know that that's what you're supposed to do. I don't know why or how to explain it. One second. Okay. Let's continue then. One second. Okay. An 8 kilogram sample of hydrogen gas and a 96 kilograms sample of oxygen gas are combined in a closed vessel where they react according to the equation above. Okay, so 96 kilograms of O2 means how many moles have been made? The amount of moles made is, so oxygen is has a molar mass of 16 grams per mole. So okay, let's just do everything in grams per mole, or like just grams, and then we'll multiply it by 10 cubed to get it to kilograms or whatever later. So just ignore the 10 cubed for now. We'll just look at the, just do everything in grams right now. And meanwhile, 8 grams, so hydrogen is 1, H2 is 2, and so how many of, like, how many moles of H2 are there? There are 4 moles of that, and there are 3 moles of oxygen too. So which means that the limiting reactant is going to be H2. Yeah, the ratios, instead of 4 to 3, the ratio is supposed to be 2 to 1, and you obviously don't have that ratio there. So H2 is limiting, and since that's the case, you can have like what? So you've got like how many moles? You've got 4 moles of this and 2 moles of this reacting, basically, instead of the 3 moles of that. And so when you've got 4 moles reacting, then there'll be 4 moles of this as well. So it should be 4. And then obviously times 10 cubed. That I'm just not saying that right now. Okay, next one. Magnesium chloride and sodium hydride react to form. I could be getting the names all wrong, but I did that chapter like a long time ago, and I forgot a lot of the stuff. I didn't take notes for that, so I don't know. Magnesium dihydride maybe, and sodium chloride. So those are the products, and the reactants I already said. So he's done an experiment to determine the molarity of the solution. He mixes 100 milliliters of this solution with excess sodium hydride, causing this to precipitate. He then filters and dries the precipitate and does this. Okay. So what's the difference here? What's the mass of the mass of the magnesium dihydride precipitate, or just the precipitate, is going to be 1.76 minus that, which is 1.16 grams. Okay, now the reason I'm like trying to write no matter how bad it is here is because this is like this requires more numbers and that sort of stuff. Okay, so that's how many grams there are, and the number of moles then is going to be, so the number of moles is going to be, and okay, one last thing, the molarity of this solution, it'll just be the same as, yeah, since they've got the same stoichiometric coefficients. This could be wrong again, they don't trust any of the stuff I'm saying here. I think it'll just be the same as the molarity of this, or yeah, it has to be because the number of moles of this is the same as the number of moles of as this, and so we know that it's in 100 milliliters, which is 0.1 liters. Okay, this is disgusting. Let me just write it like with this. Yeah, the pen is like doing it's completely useless right now, so I'll just do it like this. Divided by 0.1 liters. So this is going to be our final answer, by the way. We need the number of moles, right? The number of moles will be the same. How do we find that? Well, 58 grams. What is this? This was like 1.16. So it's going to be 56 grams per mole divided by the number of moles. Uh, or no, sorry, it's going to be this divided by the by the molar mass, which will give you the number of moles. So it's this divided by 58. That's how many moles there are. If we multiply this by, so this wait, okay, the if you multiply it by 100, then it becomes 2. So it's 2 times 10 to the negative 2 divided by 0.1, which means I'm multiplying it by 10. So it's 2 times 10 to the negative 1. 2 times 10 to the negative 1, so 0.2. Okay, good. The number of Cu2 plus ions that are produced is equal to which of the following? 4 times the number that, no, it's 1/4 of that. 1/3 the number of NO3, no, it's half of that. 2 times the number of NO2 molecules, no, it's half of that. 1/2 the number of H2 molecules. Yeah, that's it. Just look at the coefficients and then check what works there. Okay, done with this now. And so we've done stoichiometry. Now we'll do this acid-base reactions and then titration and then the unit test, and that will be enough. So redox reactions now. This shouldn't be too hard again. A lot of it will just be oxidation states. Yeah, like the first one here. So the oxidation number of which element is reduced. So which one gains electrons and reduces its charge? That's basically what it's asking. So we need the charge to get reduced first of all. So it'll either be B or D. Right? So it's either B or D. I think it's like that. It's either, yes, it's either B or D because it's reduced. Now let's take a look at chromium. Initially chromium is has an oxidation state of, okay, we need to think about this. So oxygen is -2. -2 times 7 becomes um -14, but then becomes -12 because the overall charge is -2. So it's -12 divided by 2, so it's +6. Right, so it has to be +6. Now we know the first part of this is 2. What does it change to? It does change to +3. We can see that right there. Let's check though. Yeah, so this seems correct. Okay, next. Is this a redox reaction? Oxygen is oxidized and carbon is reduced. I don't believe that, but let's do it and see. So OH has a charge of, I think it'll have to do with carbon, right? Let's just do carbon first. So over here, carbon has a charge of, has an oxidation number of +4, like right here, in CO, in carbon dioxide gas. and in CH3OH. So over there it's going to be OH is -1, so it's -2. So carbon is oxidized. So it's not this, it's not this, it's not this. So carbon is oxidized. Yeah, good. Um, okay, now for this, like to you want to combine it so that the electrons cancel on in the oxidation and reduction half reactions. So you multiply the oxidation half reaction by 3 everywhere, and sorry, and so now they're asking us for the ratio of hydrosulfuric acid and this. So it must be 3 to 1. Okay, which of the following represents the oxidation half reaction for the reaction shown above? Okay. Oxidation is the one where you gain like the state where your oxidation state will increase. And where does that happen? That happens with chromium, obviously. Yeah, it's just with chromium. So you have chromium plus 3 electrons gives you, no, that's wrong. So that's wrong first of all, because that gives you a -3 charge. Obviously the charges need to like balance out, so it should be this. It has to be that. Yeah. Okay, next. Now this is like the last one that I've done so far. And conjugate pairs. So the conjugate, I learned that all last night. So I might not remember it all. Okay, conjugate acid base pair. Oh, the only difference between them is that one has one hydrogen more than the other. So it should be, wait, let's do conjugate acid base pair, right? H2S and HS seems to work. H H2S and HS works. Yeah. Oh, OH and H2O would work as well, but that's not an option here. So basically, one of them will just be one hydrogen more than the other, which doesn't seem to be the case in the first one. Isn't the case in the second one either. No, it's not. And in the third one, oh, okay, over here. Oh, sorry, I did it wrong. It is this. You're just adding a hydrogen. I got confused with the charge over there, but obviously the charges work out because hydrogen has a positive one charge. So this is correct. Which of the following represents an acid-base reaction? So, I actually completely forgot how to do this, so we'll just see. So, there should be, some, what's it called? One side should have, you should have an acid and a base together, and then they cancel out, which is in the first one. Here, there is no acid, there's no strong acid. There is a strong acid, hydrochloric acid, but there's no base. Okay, and then here same thing, that you need like an H and an OH, and the only place where that happens is A, so it should be A. Yeah, and that happens here, and it doesn't really happen in any of the other ones, so that's good. Which of the following is a conjugate base? So the conjugate base will just have one hydrogen less, like one fewer hydrogen, which will be HbO4, and then charge is 2 minus. Which of the following correctly identifies the role of water in each reaction? So in the first one, it's a base because you're adding a hydrogen to it. So in reaction one, it's a base, and then in reaction two, it's going to OH minus. It's going to hydroxide, I think, or I think that's the right name. Which means you're doing basically you're being an acid there. So done. Okay, great. Now done with that. Now the last one is titrations. Actually, I don't know how to pronounce it because I've not watched any videos with it. Right? It's just been reading the book. So I'm saying titrations or titrations. It could be something else. Okay. Let's go with this. Now I might have to, this will require like three significant figures and stuff. So it will require a lot of calculations. And obviously this isn't going to work out properly using my pen and whatnot. So let me just use a piece of paper and a pen with me and a calculator with me. That should be easier. Actually, this pen doesn't really work either. So uh, let me check. Yeah, it seems to work a bit. Okay, now we need to figure out the molar mass of this acid. And if 45 milliliters of KOH are required to consume the acid completely, what's the molar mass? So first of all, how many moles are there of KOH? Divide that by 2 to get the moles of H2A. And once you got the molar mass, you can use the um sorry, once you got the number of moles and you know the mass, you can just figure out, divide the mass by the moles to do to get the molar mass. Okay, so let's do that then. First step is to do 2 KOH. Actually, no, how many moles are there of 2 KOH? Can we just figure that out immediately? We can, because the student iterates it with 0.215. That's a molarity. So 0.215 equals the number of moles divided by 45.1 milliliters, which is 0.0451, right? 0.0451. Okay, so the number of moles of KOH is going to be it's just going to be the product of the two, actually, I think, uh unless I did it wrong. So number of moles, that's 45 milliliters. Number of moles, okay, yeah, that seems right actually. So 0.0451 times what, 0.215, 0.215, that's the number of moles divided by 2. Now that's the number of moles you have, right? So now you know that, and the molar mass is 0.728. So divide that by the number of moles to get 150. 150 point, oh, only three significant figures. So is that enough then, or yeah, this is enough, I think. Okay, good. A sample of hydrofluoric acid, might be the wrong name again, I'm not sure. It's titrated with sodium hydride as represented by the equation above. Which of the following diagrams best represents the species that are present in significant concentrations in the mixture when the titration is at the equivalence point? H2O molecules are not shown. Okay, so titration is with, wait, I've never done a redox titration before. I don't know what titration before. I don't know what that is. So let's take a look here then. The species that are present in significant concentrations. So at the equivalence point, what happens? At the equivalence point, that, like, it's neither acid nor base, right? Like they've just cancelled each other out. So there shouldn't be any OH left. Oh yeah, there shouldn't be any OH, and there shouldn't be any hydrogen left. Actually, there shouldn't be any hydrogen at all. So there won't be hydrofluoric acid, there won't be OH here, there won't be OH here, so it should just be this one. Great, done. An acidic solution is represented above. In a titration experiment, a zero point 0.2 mole molarity solution of potassium permanganate per, permanganate is added from a I don't know that word either, the pronunciation, to an acidified sample of dihydrogen peroxide, or something like that. Yeah, dihydrogen peroxide in a flask. The endpoint is determined by the appearance of a faint pink color. How many moles are in the sample? In the sample, So first of all, that 30 milliliters that have been added, right? That's the difference between the final and initial Burette readings. So 30 milliliters, I should write this down. 30 milliliters added, or 30 milliliters needed of what? In a titration experiment, potassium permanganate is added from a burette. Okay, so it's that it's that much. And what am I saying? And the molarity is 0.02, right? So that's equal to the number of moles of potassium permanganate. So KMnO4, and where um yeah, and then you need to know how many moles of H2O2 aqueous were in the sample. Great. So the number of moles of that. Wait a second. Where is? It'll be five halves as much. I don't know what I'm. Wait. No, that seems wrong actually. Uh, so the only place I see the reaction. Oh, okay. The number of moles of potassium permanganate will just be the same as the number of moles of permanganate, which means that it should be the ratio will be five halves. So I'm guessing it's either 1.5 or 1.5% to the negative third power moles, or 1.5 times 10 to the negative fourth, because this will probably be five times the number of moles of permanganate, and this will be five times. So these will be five halves. Okay, now let's actually do it. And so the number of moles is 0.02 times 0.0, so 30 milliliters, right? So 0.03, which is 0.6 times 10 to the negative fourth, times 5 divided by 2, 1.5 times 10 to the negative third, right there. Good, we got that. Next one, a 10.1 molarity solution of hydrobromic acid, maybe, might be the wrong name, is used to titrate 150 milliliter samples of four different 150 milliliters samples. The volume of HBr required to reach the endpoint for each sample is shown in the table above. Okay, which contains the highest concentration of metal hydroxide? Metal hydroxide, right? So, well, think about it, right? To the highest concentration, we can think about this just logically. That's the point of this, to see if you already understand what's happening here, which I don't know if I do. Okay, so if you're adding the same old acid, right? And it's 150 milliliters. So if you add more milliliters of hydrobromic acid, you're adding more like acid to the thing, and it's the same like volume of each of the metal hydroxides. So what we'll do then is just, so I'm guessing already it's BA, so solution for it should be, because you're adding more acid, and that means that there's more base in your solution, right? So which one has a, well, actually, then wait, there could be like one more thing actually. The highest concentration of metal hydroxide. Over here, we've also got two bases though, right? So, I mean, we've got OH with a subscript of 2. So maybe we have to do, I'm going to guess solution 4. I think that should, okay, wrong. Then now my next guess is going to be solution 1 then. Because it's, see, this is 2. So if you like give all of them the uniform 2 over here, then this becomes 190. I'm not sure what happened here exactly. So how do we determine the ratio of this acid and metal reactant? Yeah, they react in a 1-to-1 ratio. And then what did they do here? They figured out that it's 9.5 times 10 to the negative third, 3, 4.5, 7.5. So they divided it by 2 then? Is that what they did? Yeah, they divided it by 2. They divided this, they kept this the same. They divided this by 2 as well. Or the other logic that I was saying then, that you just multiply this by 2. It's not the same mathematically, but like it'll give you the same intuition or whatever. Let's try it again using that information. So let's go. Okay, we've got a solution containing 1.08 grams of an unknown diprotic acid. To determine the molar mass of the acid, the student titrates a sample using a 0.524 molarity solution of KOH aqueous. The balanced equation is shown below. So that's a balanced equation. That means that there are 2 times as many moles of potassium hydride than the unknown diprotic acid. And the molarity, we know the molarity, right? It's 0.524. So that's just equal to the number of moles divided by 35.5 milliliters, which is, we need to put that in terms of liters. So that will be 0.0355. Multiply them out to figure out the number of moles. So the number of moles of potassium hydride is going to be 0.524 times 0.0355. I made a typo here. 0.524 times 0.0355. So we've got that now as this number here. I'll just read it off. 0.018602. Now we need to, that's the number of moles there are. Now we can divide that by 2 to get the number of moles of the unknown acid. And now if what is asking for? The molar mass. So you do 1.08 grams divided by the number of moles to get the answer, final answer of 116.11. So 116. Great. Now this one. Okay, we already know that this is an acid, right? H3O. So if you're at your equivalence point, there won't be any acids or bases left. So that won't be there. This has an OH, which isn't supposed to be there. This has an OH as well. That's not supposed to be there. So it'll just be this. You just can't have any bases or acids there. That's the root. Now this one, they're asking us for the, so okay, the difference, like the amount of the volume of the titrant, yeah, of the titrant that you're putting in is going to be the final Burat reading minus the initial Burat reading, obviously. So that's just 20 milliliters or 0.02 liters. That's a volume. And the to an certified sample of this. Okay, the number of moles of potassium permanganate will be the same as the number of moles of permanganate, and the ratio that's acting here is 5 halves, because we want to get the number of moles of H2C2O4. Okay, and the solution is 0.04. That's a molarity, so it will be 0.04 is equal to the number of moles over 0.02. If you multiply them, what do you get? You get 0.04 times 0.02, which should be 0.0008. I think that's right. 8 times 10 to the negative fourth. I'm pretty sure that's the same thing. And then now you multiply that by 5 halves. So times 5 divided by 2. So you get 2 times 10 to the negative third. Okay. Next one. Which solution contains the highest concentration of metal hydroxide? 20 is used to titrate. Okay, doesn't matter. That's what doesn't matter too much. What we need to figure out is, you know, like which one has the most. This is the same question as the last question of the last set. Very similar thing, and it's like the intuition based part or whatever. So the highest concentration, since they've all got the same volumes, we just want to find the highest molarity. of metal hydroxide, right? And so that will be with, you can basically, I want to make them all integers. I want to divide by 2. I'll multiply these by 2. This becomes 70, this becomes 120. So it's KOH, and therefore solution 2. Hi, Tommy T. Okay, next. Okay, wait, now we're done, right? So let's go on to the last thing now. Yeah, we've done everything, just the unit test is left. And since we've done like everything just now, it should be easy to recall everything. And 10 questions. Okay. Which of the following equations best represents a dissolution of dilithium sulfate in water, or lithium sulfate in water? So it's going to begin as a solid. So those are the reactants, and then the products will become. We want to balance the charges, right? So SO4 has a charge of what, -2, like that. And then to balance the charges, we'll put a coefficient of 2 on the lithium. So it'll just become this. Okay. A student is given a solution containing 0.932 grams of an unknown diprotic acid, H2A. H2A. To determine the molar mass of the acid, the student titrates the sample using a 0.481 molarity solution. So 0.481 is equal to the number of moles of KOH divided by the volume, which is 28.9 milliliters. So it'll be 0.0289. Okay, now we obviously need a calculator for this. The last thing though is that, what is a molar mass? Okay, same thing. So let's figure out the number of moles of potassium hydride, which is 0.481 times 0.0289. That's the number of moles. Now we can divide this by 2 to get the number of moles of H2A. And now we do 0.932 divided by that answer to give us a final answer, which is similar to the other two we've done, 134. Okay, good. This is not a physical change. This is a chemical change. I remember this question exactly. We just did that one some time ago. Uh, Sorry, I don't know what that means. Are you saying like talking to, or something else? Like I was saying hi to Tommy T. Oh, in the stream, I'm just like thinking aloud and stuff. Okay, a mixture of C2H4 and O2 gas is placed in a container, and a reaction occurs according to the equation above. So we've got that equation. A particle level representation is shown below of the products. So just of this stuff, let's take a look then. So water is H2O, obviously, which is, it's these small things. So there are 4 of them. So we can multiply everything by 2. That will balance it out a bit. That will balance it out. And so now we need the reactant mixture. So there'll be 2 C2H4s. C2H4 is it's this thing. So there'll be 2 of them. And the only one with 2 of them is C. So the answer for this will be C. Okay, what's a conjugate base? The conjugate base will just have one hydrogen fewer than this. So it'll just be this one. Which of the following represents the oxidation half reaction? So in the oxidation half reaction, it'll be the magnesium part. So it should be this. Just let me make sure though. Yeah, oxidation means the oxidation state will increase. So it's going from nothing to 2 plus. So that's the oxidation half reaction. And then to balance the charges, you'll put 2 electrons there. So that should be right. Okay, again, this thing. So over here, the mass of the precipitate will be 3.23 grams. And the number of, and they're 10 milliliters. So so what are they asking for? They're asking for the molarity. and there's no difference in the ratios, right? So the stoichiometric coefficient of the precipitate is the same um as of this solution, the Na2CrO4 solution that they're asking for, disodium chromate, I think. I'm not sure. So we've just got the number of moles, which is 323 grams per mole. So we'll do 3.23 grams divided by 323 grams per mole, which gives us 1 times 10 to the negative 2 moles. And then we divide that by 10 milliliters. 10 milliliters is just like what, 1 times 10 to the negative 2 liters. So we just get 1. That should be our answer here. Okay, good. Now just 3 more now, right? So uh, these reactor produces solid precipitate and an aqueous lithium chloride. Okay, so the solid precipitate will remain there. Lithium chloride. So if that's aqueous, we'll have a lithium ion, high Solivaygus. Uh, so there'll be a lithium ion there, and there'll be what's the other one? And a chlorine chloride ion there. So we have those will cancel out with the lithium and chloride in the reactants, which will leave us with just Sr2 plus. That's correct. PO4, it has a charge of -3, so that's also correct. And then this should be, yeah, this seems correct then, right? Unless we have to take into account take these coefficients into account, which, no, I'm not working for Khan Academy, but this is just like a good source of practice I found. So I'm doing this, not working for them. Actually, no, this is wrong. The charges don't balance out, so it has to be this one then, right? Because this is +6, -6, and this is neutral, so those will cancel out. So that's correct. Next one, it's a chemical process. Uh, 10 minutes. Yeah, okay. Yeah. Yeah. Okay, next one now. Yeah, chemical process. So fractional distillation is, I read about this in some other book. I'm pretty sure that that has to be physical, right? Because, like, actually, I'm not too sure. So let's just take a break. Okay, that's good to know. Chromatography is also physical, I think. Burned completely in air. Okay, if you're taking metal and you're burning it in air and yielding a new thing, then that has to be chemical, right? So it should be that. This is just changing like the state, like into a solid crystal. So this is physical. So all of these are physical, except that one. Last question now. Okay, thank you. Thanks a lot. So let's take a look at this then, right? So barium chloride, and then these are represented above, causing a precipitate to form. With the precipitate, we can see over here, it's going to be the solid, which is BaCO3, solid BaCO3, BaCO3. So it has to be one of the top two. And out of these two, what's everything else should cancel out, right? CO3. So everything else will cancel out. What am I saying? The Ba and the CO3, they'll cancel out from here. So there shouldn't be any of that left. So this thing over here should not be left. So it should be B, and that seems correct. Okay, good. Done. All of them leveled up. Okay, wait. I think then we're just done with this unit now, which is a good thing. Yeah, 100% done. Now let me think about what to do next, right? Because actually, let me open up my book as well. So it's this book right here, Zoomed Out Chemistry. The next chapter is about gases, but there's no equivalent over here. Like there's no chapter about gases here. So that's not a good thing then. Anyway, I'll read it and I'll get back later then. But I think um, that's it for the stream then. I've done How long has it been? It's been almost an hour now, which is longer than I expected. Uh, Wait, what? Are you talking about the class or wait, my grade or so AP tests? Like, uh, I don't know. I think you can take them like whenever you want. So you can take them at um you can I think you can take them in middle school. I don't know about that, but you can take them in ninth. I'm going into 10th. Yeah. So but anyway, for AP tests, you can take it. I think at any time. It's normally people take it in high school, and this one in particular, AP chemistry. I think they take it in 11th or 12th. So obviously, I don't know everything there, but I'm just trying to study ahead since I have another chemistry class next year, and just want to like know this stuff in advance so that I do well over there. It's apparently a hard class. There's only one teacher, and she's hard, it seems. Okay. Wait, are you in India or somewhere else right now? Solid Vegas. Yeah, I've been there. Okay then. So I think that's it for the chemistry part of the test. So good there. Okay, yeah, I've been to Lucknow before. I think I had it was either yeah, I've been there. I had like the pink tea over there. The okay, wait. I'm just getting a call from my father. Let me pause this then. Sorry, there was a cricket match going on, the Pakistan America match. So my grandmother was watching that, so I just had to set that up for her. Okay, anyway, it's been almost an hour now. It's like 12:48 here, so I'll have to end things soon. So actually, you know what? Let me think out some future streams or videos in general. Like I don't know how long it'll take me for chapter 5, the gases thing, and even that. Let me actually see. So that is chapter 6, chapter 5. Chapter 6 is thermochemistry. So let's see how long these are. 253 pages. So it'll be 50 pages, and then uh, a full 100 pages I have to read to like finish the next unit there, which is thermodynamics, I think. So that will take some time, and yeah, I'm not too sure how long it'll take. So I'll make another stream for that, but of course there are other things that I'll make as well, other videos. So yeah, okay. Thanks for watching, everyone. I'll see you in another video then.